So I'd like to start this occasion with the department head in MIT Chemical Engineering, Paula Hammond.
Excellent. Thank you, everyone. I am very honored to be able to introduce George Stephanopoulos to you. Of course, he is an incredibly well-known person, and to you, he is a very meaningful friend. He's a philosopher, a teacher, and an adventurer, because he has actually led the field with his vision in chemical engineering, both in process systems engineering and more generally and broadly as a leader in the field of chemical engineering. So I am very happy to thank him for all of the things that he's brought to us and to the field. Now, George has had a huge impact on the field and left a very real legacy across the world and also here at MIT, and I'll just touch on a few of those things because, of course, you'll hear in great detail about some of his contributions from Manfred Murari and also what he's done at Mitsubishi Chemical more directly from his colleagues there. However, I'd like to point out that as a person, he has been a true mentor to students, faculty, and colleagues throughout his life. A little bit about his life. He's from Kalamata, Messenia, Greece. And while he was in high school, was a competitive swimmer in high school, a true athlete. And I think this competitive spirit is something that he took with him in everything else that he's done. He entered the National Technological University of Athens, or NTUA, and joined chemical engineering on a whim, loved and stayed, and got a degree in 1970. And we're very fortunate that he decided that he liked chemical engineering and stuck with it. He went on to get his master's from McMaster University in Ontario, Canada in 1971. And then he went on to University of Florida in Gainesville in 1974, where he was involved in this very exciting environment and ended up working with Art Westerberg on process synthesis and non-convex optimization. Now from there, George joined the University of Minnesota, which was a tower of chemical engineering. It had a number of the big names in chemical engineering. He worked alongside people like ours, Amundsen and Scriven. And he got his PhD in 1974. Now, I'm sorry, he actually got his PhD in 1974 from University of Gainesville, Florida in Gainesville, and joined Minnesota in 1974. And as a junior faculty there, launched his career. After launching a career which involved engaging a number of the newest technologies, including artificial intelligence and process systems, he went back to Greece in 1980. At NTU, he actually advised a number of students, including a number of undergraduate students who have gone on to start their own academic careers. And there he also wrote his famous textbook on chemical process control. In 1984, he came back to the United States, and he came back to MIT. At that time, he started a program, a laboratory, LISP, which is the Laboratory of Intelligent Systems and Process Engineering. And with this group and this team, built a large number of exciting approaches to everything from metabolic engineering to more traditional chemical process systems. His work had a huge impact on a number of different fields. He was also of great interest to industry. And in fact, one of the things that I think is unique about George is his adventurous spirit, because he looked at such a broad number of problems from life sciences to chemical process. This led to his becoming involved in the Mitsubishi Chemical Company, first as an advisor, and ultimately in 2000, he took a leave of absence and became the chief technical officer of MCC. I think this is an incredible path for George. It's very unusual for a highly established and well-known chemical engineering professor to become the CTO of a major chemical company. But I think it really speaks to not only George's intelligence, but his vision and his ability and encouragement, spirit, in looking at new kinds of problems. Now, when he began his work at MCC, the press release described the fact that he is being charged with overseeing fundamental changes in the way their research development engineering program functions within the MCC group. During his time as CTO, he aligned the research strategy with the business strategy and essentially took the company from a process-focused company to a product-focused company. Now, during this time, I was actually a junior faculty member here and was just approaching my first promotions, and I was in awe of this chemical engineering professor who was also able to tackle these very important industrial problems on such a high level. And he often spoke with me about how we can actually take ideas that are born from biology and from chemistry and incorporate them into the way that we handle chemical engineering problems. This was something that is a theme I think we'll hear throughout the day about George, which is that he's not only a visionary, but he's a mentor, and he shares his vision with others and inspires them to do unique things and to take risks. Now, a little bit about George during his time within the department. He took that leave of absence, of course, and came back after 2 years, but continued to be involved in MCC as a board of directors, making it a total of 5 years. However, during his time at MIT, throughout, he's always been an outstanding citizen. Within our department, he introduced and developed the concept of what is now our unique capstone senior year course, ICE, Integrated Chemical Engineering, which involves 2 longer sequences that allow students to take a deep dive into a batch and a continuous process, integrating everything that they've learned in chemical engineering, from essentially chemical kinetics and thermodynamics to transport, to address a fairly complex problem. There are also ICE-T, or Integrated Chemical Engineering, topics. These modules allow faculty to take a deep dive into their given specialty in a short time frame and use, again, this integrated concept to address problems within a specific field. This has become one of the key signature notes of our chemical engineering education here at MIT. What I've heard from seniors who come out of this class is that this is when they feel like real chemical engineers. And what I saw was George using his vision to guide us toward a curriculum which actually gave back to students and allowed them to think in a way that was much more comprehensive and interconnected. George has always been a proponent for student education and a true believer in the inspiration of students, exposing the frontiers of the field and always pushing others to do the same. Within his own profession, he's been an outstanding steward. He was the AICHE CAS Division Chair, the AICHE Journal Associate Editor, and he held many other positions within AICHE. Among his many awards and recognitions, he was elected to the National Academy of Engineering in 1999, the American Academy of Arts and Sciences in 2012. He was a foreign member of the Russian Academy of Technological Sciences in 1991, and he received an honorary doctorate from McMaster University. The AICHE has honored him many times for his contributions, including, as a young professor, the Coburn Award in 1982, the Walker Award in 2003, and the Founders Award, our most significant award in AICHE in 2012. He was also the Institute Lecturer in 2003, and he was listed among the 100 chemical engineers of the modern era in AICHE's 2008 celebration of chemical engineering. In addition to his many other recognitions over the years, of course, he has given many honorary lectures, and he's been recognized by both universities and industry. George is indeed someone who has given incredibly to his field. He is someone who is a contributor, someone whom we will always remember, and he has a huge legacy. I am so amazed and proud of his family tree, of the wonderful colleagues who have come out of his work, and the contributions that he has given that will continue in our field for many years. So with that, I'd like to welcome George and all of you to this wonderful symposium in celebrating his life. Thank you, George.
Thank you, Paula. A few words about safety. So you've all walked in here, but that's okay, I'll walk through it anyway. So the exits are right here on the left, and if the fire alarms go off or whatever, then just go down the stairs and out the door there and cross the street. So now we have that out of the way. Oh, sorry about this a little bit. So welcome to the 24 Visions of Process System Engineering. Of course, this is to honor George, and so we also have a nice set of presentations in his honor, but also to give a good feeling about where the field's going, or we may go, or hopefully will go in the future. Another way of saying is a symposium on future product design, complex system, mathematical modeling process. There's a long list that we're going to cover in the next 2 days, and I'm sure it'll be very intellectually fulfilling. And I look forward to the next 2 days of presentations. On that note, I'd like to introduce Frank Doyle, who's the Armstrong Professor and Dean at Harvard University. He got his PhD with George in 1991 at Caltech. And then, Manfred. George Jr., I meant George Jr., sorry, I forgot the junior there. So, then he became a faculty member after going to DuPont for a year at Delaware, Santa Barbara. Purdue, Delaware, and Santa Barbara before moving to Harvard, where he's now the Dean of Applied Sciences Engineering. Frank?
Thank you, Richard. It's a pleasure to be here, and as you'll see in the format here, I'm actually the first of George's academic grandchildren who will be chairing the sessions over the course of the next 2 days. So, Grandpa George, it's a distinct honor and pleasure to be here. And it's highly fitting that, in fact, the first speaker I'm going to introduce was George's first PhD student at the University of Minnesota and my mentor at Caltech, Manfred Merari. Manfred is arguably one of the most celebrated academics in the field of systems and control. He has been recognized with almost every major award that the field has to offer. I'll call out just 2 of them. He's a member of the US National Academy of Engineering, as well as an international fellow of the UK Royal Academy of Engineering. Manfred began his academic career, his undergraduate work at ETH, before going to Minnesota to pursue his PhD, working with George. From Minnesota, he went to Wisconsin, where he was on the faculty for 6 years, before transitioning west to Pasadena, where he started on the faculty at Caltech, which is where Richard and I and a number of folks in the audience had the good fortune to work with Manfred. He became eventually the executive officer of chemical engineering at Caltech, the equivalent of department chair, before moving to ETH, Zurich, in 1994, where he took up the head of the automatic control laboratory within the Department of Chemical Engineering, as well as the chair of that department. Following that career in 2016, a year ago, he retired, which shocked many of us, and we couldn't associate the words retire with Manfred. So of course he didn't actually retire. What he did was took up now a new career at the University of Pennsylvania, where he has been a distinguished faculty fellow on the faculty at UPenn. So without further ado, I'll invite Manfred for his talk.
Good morning. I'm impressed by the number of people here, and I'm extremely pleased to see many of this George's family, many people that I hadn't seen for decades, some of them. I'm honored to be invited to be here and also to present this opening address at this wonderful symposium. As you heard from Frank, I was George's first PhD student. So on the left here, you see George when he graduated from high school in Kalamata. In the middle, you see George as he looked when he graduated from the University of Florida, and that's how I met George. That's how he looked. When I left Minnesota, that's how he looked in the right picture. See, he lost some hair. I hope it was not only due to his first group of graduate students. This period in Minnesota, I wrote here George's formative years. It was certainly my formative period, and George played a key role in that. The years of Minnesota for me were a life-changing experience, and I'm sure that many undergraduates and graduate students, many of whom are here today, will agree with this assessment. The years at Minnesota were tough. Actually, this first semester at Minnesota was probably the toughest year I had in my life. It was one of those few periods where I said, if people had asked me to do more, I said, no, I cannot do more. We were all at the limits, and I think that was typical for the students at that time. But we also had lots of fun. And actually, one of the most beautiful memories is that in 1977, the American Control Conference, I think at that time it was still called the Joint American Control Conference, took place in San Francisco. And George decided, maybe also for financial reasons as a young assistant professor, that we would drive from Minneapolis to San Francisco. And so we drove across country in his beautiful Lancia Beta, that was his dream car. And we drove to Mount Rushmore, Yellowstone, Tetons, Salt Lake City, Reno, Pasadena, San Francisco. It was absolutely wonderful. Obviously, there are other, I have to find my mouse here. Okay. Obviously, there were other nice anecdotes. One characteristic episode I want to tell you about, but in order to appreciate it, you have to understand how the office setup was for us in Minneapolis. So there was a hallway that you enter, the small hallway. The first was our office, me, Yamana Kuhn, and my office. Next was another graduate student office, and then was George's office. And there was some waiting area with a sofa. And this date, June 1, 1977, was an important date that we all remember, and certainly Yaman will remember, because it was George's 30th birthday. Okay? So the day is exactly his 70th birthday. And we remember it because I was usually coming late to the office. Yaman was early. And at the time I came, felt there was perfume smell in the air. A female well-wisher was sitting on the sofa in front of George's office. Yaman smilingly told me that this was the fourth. Two had already left. One was meeting with George at the moment. And let's just say George was very popular. Not only with the students, but also with friends, a lot of friends. But I have only 30 minutes, therefore I will leave more George's stories for later. We have 2 more days. But I want to talk a little bit about the title. First of all, process systems engineering, visions for process systems engineering. As Frank alluded to, I really moved out of process systems engineering some 20 plus years ago. The slip of the tongue of Frank, I did not move to chemical engineering at ETH. I actually have been in electrical engineering for the last 20 plus years, so I really haven't followed everything that's going on in process control over those years. So I will focus on the process control part, or more specifically on the control part only. The second thing is George's impact. I can't possibly do justice to that in the time I have available. Fortunately, you heard already about it in the presentation, in the introductory presentation. But let me give you the outline here. So after a few slides setting the stage, I will focus on the time when I was working with George. And then as the next thing, I want to briefly remind you of past attempts that were made to predict the future in process systems engineering or in process control. And learning from this experience, I will limit my predictions to the assessment of the current trends, and I will leave it to you than to speculate how those current trends will continue. So my time with George, as you said, as you heard, started in 1975. George had just arrived from the University of Florida, and it was a little bit too risky for me to choose an advisor who had just started his career, so we both agreed that Rutherford Aries would be my co-advisor. I actually received this picture here from George. I received it 20 years after it was taken in 1995 for the graduate brochure. It had an accompanying note that said, do you have this photo? Wow, I had forgotten how better certain things looked 25 years ago. Now, when I showed this picture to my kind wife, she said she didn't know what George was talking about. And I decided to leave it at that. This gives you a slight impression on how computing looked at that time. This was actually before. That was the first digital controlled computer introduced in 1964. This is more like what we had at Minnesota. Not exactly. We used CDC equipment because Control Data had its headquarters in Minneapolis. So this is approximately how our computing sources looked like. In terms of the theory setting the stage, there were some textbooks around that time. I'm putting up those two, Morton Den and Harmon Ray. I'm putting up those two because both of them were graduates from Minnesota. Both of them had Rutherford Aries as their PhD advisor. If you talk to them, both Morton and Harmon, at that time, book came out a little bit later, you would have heard some frustration about the lack of impact of their work or the lack of adoption of their work by industry. What happened in terms of the computing resources at that time is apparent from my stay that I had at Exxon in 1978. 1 week, people were very excited to get new process computer equipment. The next week, they complained because all the new capacity was used for user interface, and what was left then in terms of computer power didn't allow much more than implementing PID controllers. So the frustration was not only when you talk to those people, but they actually did something about it. And at that time, there were many analyses of what had gone wrong. And here's a list of the most important ones, a review paper by Alan Foss in '73, another review from industry for mobile, which supposedly actually was ghost-written by Ruel Chenard, a paper by Ruel Chenard. And this unhappiness was not only limited to chemical engineering, but it also was electrical engineering. Here, the title of a very controversial paper by Isaac Horowitz and Uri Shaked, again at the time that we were studying at Minnesota. Those papers were our daily reading material where we looked to identify deficiencies in the field and to gain inspiration. And actually, the culmination of all those critiques was the Chemical Process Control Conference. The first Chemical Process Control Conference was organized by two of the people I just mentioned, Morton Den and Alan Foss, and the basic spirit of this conference was that explosive developments had taken in industry, but the academics said industry had no understanding of all those developments, and the industry people responded, academia had no clue about real control system design. It was a watershed event. These proceedings were published later, but we had Xerox copies, and in George's group, we devoured that material. At this point, I would say, enter George. Okay, so what was his response to all that? I think typical for him, research community is studying the wrong problems. So much of our time at Minnesota was spent finding and defining the right problems. And the timing for that exercise was good, but I think most of us at that time didn't know where to start. And here I have some quotes to that situation by Richard Hamming. So if you do important work, then you must do it on the right problem, at the right time, and in the right way. Without any one of the three, you may do good work, but you will almost certainly miss real greatness. An important aspect of any problem is that you have a good attack, a good starting place, some reasonable idea of how to begin. Timing was good, but they really did not know where to start. George's method was the Socratic method, learning by debate. And what this meant for Yaman and me is that we were arguing with George on an almost daily basis what was worth working on and how to approach those problems. And for us, I feel this was probably the most valuable part of this experience at Minnesota, and it really prepared us the best for our subsequent careers. So for us, I think that quote from Arthur Ashe is very applicable. Success is a journey, not a destination. The doing is often more important than the outcome. So the difference that we decided to set was that we did not want to focus on controller design and controller tuning, which was typical at that time. We decided to focus on architecture, on structural decision. And we developed a method also as a second point to judge the controllability of different control alternatives. So here, some of the contributions from the time. So we studied how to decompose control tasks separated into multi-layer, multi-echelon decomposition. It's also interesting how vocabulary changed. Multi-echelon was typical at that time, that nobody uses that today. As I said, we spent arguing, and if you look at this diagram, you see the multi-layer, multi-echelon decomposition. I wrote here arguing. This was a very mild period here when we had this picture taken for the graduate brochure. But actually, George had started working on those ideas of decomposition during his PhD with Art Westerberg, and I'm very happy to see Art here. And George wrote this paper, which is probably his most theoretical paper, together with Art, where they talk about Lagrangian decomposition, they talk about methods to resolve the dual gap, destroying the separability of separable systems, as indicated in the abstract. Many people at that time were interested in optimization and decomposition. So there's one book here on the left by Mesarovic and co-authors, which was on the theory of multi-level hierarchical systems, very much quoted. There's a second book here, German translation by somebody called Wladislaw Findeisen. He was leading a group in Warsaw that had strong interactions and exchange with the group at the University of Minnesota, and there are other books that I have pictured here as well. Interestingly, a few years later, I would say that this area, at least from my perspective, was abandoned. It was, at least on part of some people, it was almost despised because they said, why are you doing this? Decomposition ruins the convergence properties, and how you are going to actually implement that. You have to think about what was the implementation here. The implementation was on mini computers. Okay, so you could not really afford to buy 10 mini computers to solve one optimization problem with the communication. So I'm not aware that anybody seriously used those techniques, and it was a mismatch between, on one hand, the theory, and on the other hand, the hardware that was available at that time. Greatly, this area came back with a vengeance. And George was way ahead of his time. Why did it come back? Because now we have the hardware. okay, in order to do this decomposition and use that decomposition in order to address optimization problems. And the second reason is that now we really have problems that are too large to solve in any other way, and this is the major change. And so in some sense, George and certainly also Art were way ahead of their time introducing and working on those methods in the mid-1970s. We also studied control structure decisions using this concept of structural controllability. Really, if you look at subsequent papers here, a review paper in Automatica, for example, you see that many of the dozens, I would say almost 100, work in this area subsequently makes reference to this early work that was going on in George's group in the mid-1970s. And even Sigurd Skogestad's great contribution on this control structure design for chemical plants, again, referenced this work as studying a series of contributions that influenced most of what came afterwards. The second thematic area listed here was how to design systems that are easy to control. And this was some criticism that was made in many of those review papers, several of the review papers that I mentioned before. And actually in the paper that Yaman found at the time that we were students, this was an idea that went back to Ziegler and Nichols, and not to the Ziegler-Nichols paper about PI controller tuning that we're all familiar with, but another more obscure paper. And there, Ziegler and Nichols write about the recovery factor, a complete expression for controllability is introduced, which makes possible a classification of processes in dimensions of the process itself, regardless of the controller or the valve mechanism used. And so what was a very wise idea. You don't want to assess controllability by doing some feedback design and doing some simulation. You actually want to identify the process characteristics which limit how well the process can be controlled independent of the controller you may decide to use. The only other work that I'm aware of before George and his group got involved in this area design for controllability is a paper by Jim Anderson, who was at ICI and whom I met maybe 10 years or 15 years after this paper was written. But it was very influential, that idea. And actually not only followed special sessions at conferences, but whole workshops were dedicated to this topic of design for controllability. Some of them mentioned here, so workshop headed by John Perkins, another one headed by Evangelos Zafariou, who is here, and another one, again, organized by one of George's students. So with that, I want to move on, and I want to talk about a couple attempts. One attempt that I'm aware of was made to predict the future of control, just as an example, and some of the older ones may remember that. It was a video that was put together by Digital Equipment Corporation in collaboration with DuPont. It was shown first time in the 1991 Chemical Process Control Conference. It was a big event, I remember. It was top secret what had been put together there, projecting to the future. And you see, if you look at this, it's a little bit Star Trek-like, and you can see here, if you replace this, even in terms of the garb, it is very much in this spirit. And so what, and if anybody wants this video, I have a copy, but what were the main points in this video? It talked about technological development. So one was voice control of equipment of the computer that was exemplified there. It was fingerprint identification. It was video phone a la Skype. You see that in the left corner of the screen. And it was those expansive operator screens that they envisioned for chemical plants, like shown here on the right bottom corner. But from today's perspective, I would say, and even then at that time, it was really less than revolutionary. Actually, it's interesting that digital equipment, that was 1990, as you know, missed the whole microprocessor revolution to follow. It went out of business within a decade, and after 9 years later, it was sold to a Compaq bought digital equipment. And with that, the whole computer industry in New England disappeared. And so given this an example, I will certainly refrain from trying to make predictions because they invariably will be wrong. So instead of that, I will limit my remarks to assess some current trends, and those are facts, and I will leave it to you how to extrapolate them. So let me start with a very positive statement. In the last 40 years of my career, starting with George, I have never seen the interest in control general, and I cannot speak for process control specifically, as high as today. Okay? And I'm talking about the job market, academic, industrial, at the MS level, at the PhD level, all sectors, Europe, United States, everybody is looking for people who know about control. Student interest, public interest, just to give you an indication of how that interest changed, and just as an attempt on some statistics, let me show you here graduate course enrollments at ETH, where I just retired, between 2008 and 2015-16, the last time I taught the model predictive controls at ETH. When I started there in 1994, we had about 15 students taking the class. Last spring, 150 students signed up for the course. Obviously, this was not my doing. That was a general trend, and you see it for the other courses like linear systems taught by John Laguerre or dynamic programming. They all use Dimitri Petsekas' book, and actually you see this is a spike on book sales on dynamic programming here. Second point, interest in computer science is probably an all-time high. The numbers for the whole US, I'll give you just numbers for Caltech that I happen to have available. So those are the increases in computer science, major and minor, over the last 6 years. Okay? So what's the situation now? There are more majors in computer science than electrical engineering, mechanical engineering, and physics taken together, which puts clearly a strain also on the educational system. What other issues should we comment on here in the context of computer science? For many years, control researchers complained that you look at the control system and the public is mixing up control and software. Okay, so we wanted to distinguish ourselves that the computer scientists, they're we the control engineers. That distinction has gone away. Okay? So it's not anymore control versus software. It is control and software. And students nowadays, for most application area and control, have to learn about software. They will have to write software, or they will have to supervise teams that do software for control. It has to be part of the control curriculum. Now, how much is it true for process control? I don't know. I remember that whenever it was some 20 plus years ago, Dave Smith from DuPont mentioned anybody at DuPont writing code is fired. Okay, that was at least their needs, their situation at that time, because they were using all canned programs, and that's all they were supposed to do. Certainly in other application areas, that situation has changed dramatically. Next comment, how are companies trying to hire people in control? Most of them have a hard time. Why? Because the most attractive jobs are in research labs, Google, Microsoft, Apple, Facebook, and those organizations have replaced organizations like Bell Labs or the DuPont experimental station. Also, traditional systems engineering companies have trouble finding people, and they are not competitive because of location, type of work, and salary. And universities have trouble filling positions, faculty position in computer science. Exemplary for this trend, those are the students of Ralph D'Andrea, who was my faculty colleague in mechanical engineering, working in the area of robotics. You see what his students did after graduating. There's nobody going to traditional industry. They went either to startups, a couple went to faculty position. That's not typical, but that's the current trend. Is it good or not? Leave you to judge. Is it sustainable? You will have to decide. I think market forces will determine that. Next comment, interest in predictive control, all-time high, okay? Now, in the 80s, predictive control was considered a process control hack, okay? Now that's embraced. Just came back from the American Control Conference. Jim Rawlings there gave a plenary on predictive control. Just a short survey, 65 of the 900 papers there were on predictive control. But it is, however, not traditional model predictive control as we know it here from the process industries. It is something else. And here's some example, again, from Ralph D'Andrea's lab, student Mark Muller, who is now faculty at Berkeley. The problem is for a quadricopter to return a ball to the human thrower. And as you can see, there are different ways of doing it. Either you intercept that ball early, you predict the trajectory of the ball, you either intercept it early or later or too late, like indicated here. So how is that problem solved? Actually, each 20 milliseconds, 10,000 alternative trajectories are proposed, are evaluated, the best is selected, control action implemented for 20 milliseconds, and then continued. That's a setup, position detection to those cameras, and then control via a radio link. I will just show you the short video. Sorry, that was not what I wanted to do. A short video here.
We have developed a system that allows a quadricopter to return a ball thrown by a person. The system first predicts the flight of the ball and then generates a trajectory for the quadricopter such that it hits the ball back towards the target.
That's from the view of the computer.
We show a method that allows us to generate hundreds of thousands of trajectories every second and to try many different ways of hitting the ball back towards the target. Each of the blue ghosts shown here represents one possible way for the quadricopter to fly and intercept the ball. The red ghost shows the best trajectory that we found, while the predicted ball path is shown in green. Every 20 milliseconds, we predict the ball's flight and generate about 10,000 trajectories to hit the ball. From these different possibilities, we take the best trajectory and apply 20 milliseconds worth of commands. We then repeat the entire process 20 milliseconds later. This allows the system to cope with errors. For example, if the ball doesn't fly exactly along the predicted trajectory. It also compensates for the discrepancies between the mathematical model used to generate the trajectories and the actual quadricopter.
Okay, so this is an MPC problem, but not in a traditional way. And also our theory that we do in the process control context of asymptotic convergence, etc., is not relevant necessarily to areas like that. And so many of the ideas have to be rethought, but the main concept, predictive control, is used in those areas. Let me finally just mention briefly some trends in optimization in software and hardware. First, about optimization software, just to give you a sense of how things changed in those last 30 or 40 years. Here, a slide from Jeff Linderoth, presented at the last CPC from the University of Wisconsin. The first people that I know in this room who used integer programming, I believe, was Ignacio Grossman, Rex Reklaitis, some 40 years ago. Okay, it was considered absurd. Now, how did things change in the meantime? In the last 30 years, basically, the simple analysis here says that the speed solving those mixed integer programming problems has increased by a factor of 2.5 billion. Okay. And so that means the whole area, the possibility, the type of problems that can be addressed has changed fundamentally over the our career. Now, those problems are now used. There was a fantastic talk by Russ Tedrick from MIT at a recent conference in Pittsburgh, titled Convex and Combinatorial Optimization for Dynamic Robots in the Real World. Absolutely fantastic work on bipedal robots. The main point I want to emphasize here is just the last line in this slide deck. Almost everything the robot does is formulated as an optimization. For me personally, a triumph for optimization-based synthesis. And I think we're seeing here only the first part of the development. Second, obviously everybody talks about data connectivity. I'm not sure yet if we are there in some of the industry that at least I'm working with. What is the problem? They don't have big data. Actually, they don't have enough data. That's true for areas also outside our regime. There is the Institute of Institute of Data Systems of Society opened at MIT recently. Medical people stood up. Big data? We would love to have big data. We don't have big data. Okay? So I think the revolution will be coming. It's will be restructuring type. It will be transformational, but we are clearly not there yet. Last problem here, complexity, how to deal with it. This is an old paper before autonomous driving was around. Harvard Business Review complaining about complexity, pointing out the challenges. Challenges, how much of a code you have in vehicles. Again, almost 10 years back, typical average luxury automobile, 100 million lines of code. Okay? Now with autonomous driving, a lot more than that. Are there problems? Definitely there are. They cite recalls increasing proportionally to that. You have heard about the accidents with Uber cars, with Tesla cars, etc. Recently, we'll have to find methods to deal with those challenges, and there are methods being developed. I'm citing here some work by Alberto Ferrari at Alice in Rome, and the laboratory where they actually have automatic methods for embedded software verification of fantastic magnitude. Here they take 250,000 Simulink blocks, abstract it, do some analysis on there for specific systems like electrical systems. This has not worked for chemical systems, not worked in other areas because the abstraction is managed. So again, a great challenge looking forward to. Finishing up, summary, status of trends. One sentence, it could not be more different than it was 40 years ago. When the outlook for process control, as depicted in this chemical process control conference report, was uncertain, to say the least. And George was there at this critical moment, and he got us back on track through his unconventional ideas, through his inspirational leadership, and his unique charm. Many people have gathered here not only to wish you a happy birthday, George, but to thank you for your friendship and the influence you have had on our lives. Thank you, and happy birthday and happy retirement.
Thank you.
All right, thank you, Manfred, for an amazing opening address here. We have time for one or two questions from the audience. Maybe I can lead with one. Manfred, you opened by speaking about the gap that was addressed in CPC1. Could you comment on your perception of the gap, whether it exists or has been removed in the current state?
I think that's an excellent question, and it was not set up, but it reminds me of one statement I wanted to make, one thing to relate to the audience about this gap, and that is quoting my current boss, Vijay Kumar, the dean at Penn. Okay? He's working on robotics, aerial robotics of the type that you saw here from Raf D'Andrea. Now, Vijay said, it's not a problem of the gap, okay? Our problem is the following. If we do something that is in some way relevant to industry, then organizations or companies like Google or Facebook are going to jump at it. They're going to throw resources on that problem that we cannot match. So from the beginning, we have lost. So our challenge is not the gap, that we're suffering from the gap. Our challenge is we have to generate a gap to be competitive. We have to look enough forward in the future and work on problems that are not of interest yet, because industry will otherwise beat us. Okay? So it has changed, at least in the robotics area, dramatically.
Terrific. Any other questions out there? If not, please join me in thanking Manfred again. Okay, our next speaker is going to come from another phase of George's career, and this was his stint in industry. Mr. Eiji Tanaka is the man to whom George entrusted in 2002 the management of STRC, which was the Corporate Science and Technology Research Center for the group of companies that comprise Mitsubishi Chemical. His tenure as general manager of STRC was very successful, and in 2004, he took over the management of the Science and Technology Office. This was the corporate strategy group for the creation of new businesses of Mitsubishi Chemical Holding. He was promoted to executive officer of Mitsubishi Chemical Holding Corporation, and in 2009 became the deputy director and member of the board of the newly established Kaiteki Institute. The following year, he was promoted to the executive director of that institute, and in 2015 became advisor to Mitsubishi Chemical Holding Corporation and a member of the executive committee of the Japanese Council on Competitiveness. Mr. Tanaka received his BS and MS degrees in chemistry from the University of Tokyo in 1972 and 74, respectively. Please, Mr. Tanaka.
Thank you very much, kind introduction, Professor Doyle. And thank you very much for giving a chance to talk about Professor George Stephanopoulos. As Professor Hammond introduced, Professor Stephanopoulos was working as a CTO at Mitsubishi Chemical Corporation, MCC, as a CTO in early 2000. And I was work under him while he worked at MCC. So today I will give a talk, excuse me. Okay. Titled George-san, our CTO, his work and legacy at MCC. And also, in the last part, I will talk about our vision for the sustainable future at a chemical company. On July 4th, 2000, Mitsubishi Chemical surprised the world by inviting Professor George Stephanopoulos from MIT to assume the position of CTO for the group of companies of MCC. They were surprised and curious because it was the first time for the Japanese corporation to invite the non-Japanese for such a position. His mission was to reform the structure and the culture of the R&D organization of MCC and to improve the effectiveness of technology generation for new business development. The situation in Mitsubishi Chemical in July 2000 was as follows. Profits were low and decreasing. One of the main reasons was the Asian financial crisis of 1997. Investment by the business division and capital expenditure and R&D were declining. The corporate management of MCC wanted very badly to generate new revenues and profits by the new business activities. The enthusiasm of researchers for commercializing the technology and the development was rather low. So Joseon started by reminding the researcher that the purpose of MCC was to serve the society and make money. So from the beginning, Joseon's favorite phrase was "show me the money." Many researchers suffered from this phrase, but they were able to learn quickly that the researcher's mission is not only to develop the new technology, but also to achieve the profitable commercialization. The R&D organization of MCC was divided into two parts. One under corporate direction focused on midterm technology for new business development. The other came under the direction and management of business segments focused on short-term technology needs of their customers. There were two organizations in corporate R&D sector, STO and STRC. First, Science and Technology Research Center, STRC, was a corporate R&D organization. Its mission were group-wide coordination and execution of R&D and creation and enhancement of common core technology and new product incubation. The research members of STRC was organized into 21 basic technology labs. All members belong to technology lab. The manager of each technology lab is responsible for two things. One is to enrich the technology in his or her laboratory. The other is to promote the education of the skills of each member of the labs. All the R&D projects are carried out by project teams. The members of the teams were selected from each technology laboratories, and the researcher brings the necessary skills needed for the successful completion of the project. The project leader has exclusive rights on project management. Corporate Science and Technology Office, STO, had two main responsibilities: plan and promote new business developments through new technology, and plan and execute group-wide R&D strategy. STO integrates marketing, business, and technology development. This integration was done within the STO project teams. STO project teams has two co-leaders, a business leader and a technology leader. The business leader interacts with corporate marketing, branch offices, strategic customer, and companies in MCC groups. The business leader identifies the business opportunities for further examination and promotion. The technology leader identified the necessary technology for the promotion of a business idea. This technology comes from outside or inside STRC. This slide shows alignment of corporate business and R&D strategies. In response to corporate business strategy plan by corporate management, CTO makes the corporate R&D strategy plan with STO. Based on this R&D strategy plan, the real R&D plan inside and outside MCC were made. This is a list of STRC's early days R&D projects aimed at new businesses. The project with a blue square is aggregates of several sub-projects under common themes. The projects marked with a green circle were smaller and had a single target. The projects with orange circle were exploratory. The projects shown with red character were projects at least once commercialized. Joe-san believed strongly that the most of the ideas come from outside. So from very early, he pursued the formation of alliances with external research organizations. In 2001, he created Mitsubishi Chemical Center for Advanced Materials at University of California, Santa Barbara. So it focused solid-state lighting, battery materials, solar cells, and organic transistors. Thanks to Joy-san and a professor of UCSB and the director of the centers, Dr. Glenn Fredrickson, it is still in operation even after 15 years. It has produced many patents. The second alliance was pioneering alliances for Japan. It brought together one Japanese university and 5 Japanese companies, including MCC. So many things have changed at Mitsubishi Chemical since Joe-san arrived in July 2000. For example, a holding company, a Mitsubishi Chemical Holdings Corporation, was established. And in this April, new Mitsubishi Chemical was born by merger of old Mitsubishi Chemical and Mitsubishi Plastics and Mitsubishi Rayon. However, certain aspects of the works that Joe-san introduced in MCC have endured. Let me give you an idea of the most important aspects of Joe-san's legacy at MCC. Today, the research at MCHC became much more sensitive to make money. The concept of innovation was recognized broadly in MCC, and the company and the researcher maintained the extrovert attitude and have even expanded it. We started many projects under the leadership of George-san. Some went well, and some other businesses were short-lived. But yet, we could develop several new technology and businesses. And even after George-san left, we continued to expand the technology and the businesses. And now they are those which represent MCC. Let me explain a few examples from this slide. The first example of George-san's legacy at MCC was the new adsorbent project. Zeolite technology and business grew from this project. Now there are many zeolite products in the environmental and energy markets. In this project, we have developed new zeolite called Alpo with tunable microporous structures and named it Axor. The first application of Axor was adsorption heat pumps, which is regeneratable with low temperature waste heat. The selective catalytic reduction catalyst for NOx removal was a second application. The catalyst especially shows the much less degradability after aging than conventional catalysts. The third application was zeolite membranes for industrial use. The brand name is Zebrex. It is used for solvent recycle or dehydration of bioethanol and the separation of natural gas. The Conca is the brand for food processes, like wine or Japanese sake or other alcoholic beverage and fragrances dehydration. The second example was SLPP and transparent soft polymer project, a metallocene catalyst technology for olefin polymerization and the high value added polypropylene business grew from this project. MCC and the Japan Polypropylene Corporation had developed a unique metallocene catalyst with dual function support activator and 7-membered ring metallocene. In this project, a number of metallocene ligands were tried to control the structure of polymers. Now, Japan Polypropylene has these high value added polypropylenes. These products are pivotal in petrochemical growth strategy of MCHC. On the other hand, the post-metallocene catalyst was studied through the research alliances with Cornell University and UCSB. Now the copolymer of polar vinyl compounds and alpha olefins were under development. In the past, it was a dream to copolymerize polar vinyl compounds and alpha olefin with transition metal catalysts. The third example of George-san's legacy at MCC was GS-PLA project. GSPLA is an abbreviation of Green Sustainable Plastics. But actually, many researchers said that GS is George Stephanopoulos plastic. Bio-based polymers technology and business started from this project. Now the goal of MCC in this area is to replace 20% of raw materials from exhaustive resources to sustainable or renewable resources by 2025. In this project, biodegradable polyester of succinic acid and 1,4-butanediol was studied, and also synthesis of succinic acid from biomass, and its purification was studied. GSPLA business started under the name of BioPBS in 2011. Durabio was commercialized in 2012, and Benebiol in 2016. Durabio is a kind of a polycarbonate, and it is applied to displays or automobiles parts. Benebiol is a group of diol monomer or polymers, oligomers for polyurethanes. And this concludes the story of George-san's work and legacy. From this slide, I will talk about our vision for the sustainable future of the chemical company. Our vision for the future is that we will be the Kaiteki company. So, what is Kaiteki? Kaiteki's word originated from the Japanese word kaiteki, which is equivalent to comfortable or pleasant in English. But here, our kaiteki means a sustainable condition which is comfortable for people, society, and the earth, transcending time and generations. To implement Kaiteki, we have established 3 guidelines for the judgment of corporate activities. We do not conduct corporate activities that violate the following guidelines. As for sustainability, we will reduce environmental burden and promote energy saving and conversion to renewable resources or new energy source. As for health, we will contribute to early care and health maintenance, healthy aging, in addition to disease treatment. As for comfort, we will contribute to creating a more pleasant society and comfortable living. Here, I will briefly mention the Kaiteki Institute, at which I am now working. It was created by Mitsubishi Chemical Holdings Corporation to support the implementation of the Kaiteki concept. It is a think tank for strategic advising and also an organization for virtual, global R&D and corporate identity. It anticipates the human future needs and the needs of future technologies, and also spreads the message of Kaiteki to the world. With this slide, I'd like to claim that chemical companies are solution provider to the global agenda. You can see the figures in each items are increasing significantly. For the energy demand, we supplied parts for solar or wind turbine power, lightweight parts for cars or aircrafts. We will contribute to hydrogen society. In the water and food area, we have been supplying fertilizer, agrochemical, and varieties of crops. We also supply water purification system, water-saving agriculture, like plant factories. For the aging problems, we will provide pharmaceuticals, vaccines, and preventive healthcare solutions. In connection with urbanization, we provide the members zero energy building or the smart cities. This is a list of future business and technologies of MCSC that meet KAITIC guidelines. The carbon fiber composites and the gallium nitride substrates were very useful for energy saving. We are expanding bio-based polymers with cells, the plant factories. The lithium-ion batteries parts are growing with the growth of electric vehicle. And these are the organic air materials and organic solar cells. We are developing the healthcare monitoring devices and regenerative medicines. The final one is artificial photosynthesis research. George-san arrived at MCC at a very difficult and critical time. He brought to MCSC the enthusiasm and inspiration. We did a lot starting 70 years ago. Today, we have progressed much more than we anticipated 70 years ago. The Mitsubishi Chemical Holdings Corporation is very strong today. Our future looks even brighter. So thank you very much, Joy-san. And thank you very much for our attention.
Thank you, Mr. Tanaka, for a wonderful presentation. I'd like to open the floor for questions. Quiet group this morning. Oh, in the back there, yes?
I suppose that the news of the new CEO was very surprising or shocking for the people in Mitsubishi Chemical, because not only because he is a foreigner, but also he is a professor and studying chemical engineering. For business side, big name in business companies like Karlsruhe in Nissan seems suitable. And for researchers, probably the researcher in Mitsubishi Chemical is a chemist studying organic chemistry or inorganic materials. So I'd like to ask you, why did Mitsubishi Chemical choose the Professor Stephanopoulos? He's in academia and studying about chemical engineering.
Were you able to hear the question?
I almost understand. Maybe you know, to produce the chemical products, we have a big plants in many places in Japan. So to add the told will be discussed in this symposium. The chemical engineering is very important for the chemical companies. And Professor Stefanopoulos was long communicate with Mitsubishi Chemical, and he, although he is a chemical engineer, but he knows many things. For example, he, before becoming a CTO, he was advisor of Mitsubishi Chemical Life Science Institute for the bioengineering or biochemical or many things. So he knows not only chemical engineering, but also not everything, but many things. So that's the reason why we welcome to Mitsubishi Chemical.
Terrific. Okay, one more question. Paula.
Yes, I was wondering, and this may be a question that shared with George, but how you were able to actually change culture. Were there things that you did or implemented that were done or implemented to help adapt to the culture, which clearly was important in that cultural shift from one organization to the other?
So at that time, the researcher rather interested in development of technology itself. But we are not an academic researcher, but we are the company man. So we need to have a more intention to commercialize the technology we are now developing. So in that point, Joe-san changed our mind. We are more focused on the technology rather than business. So that's the first point he changed. And also, most of the Japanese company people like to develop by ourselves, not to collaborate with external researcher. So the second point is that point. We changed to go to the outside.
Perfect. Well, please join me in thanking Mr. Tanaka for a very interesting talk. So we'll continue to sample different parts of George's trajectory with our next speaker, this time going to the late 70s and back to Greece, where Yannis Kevrakidis was a student, I'll let you figure that out, at NTU in Athens while George was back there. Yannis got his diploma in chemical engineering in 1981. From there, he went to Minnesota. One can't help but wonder whether George had an influence or a nudge in that. He got his master's in mathematics and a PhD in chemical engineering. Of course, we're all familiar with Yannis's beautiful work in the analysis of complex systems, from looking at patterns in heterogeneous catalytic systems, nonlinear system identification, and looking at computational problems associated with very nonlinear multi-scale systems. His work has been recognized by numerous awards. I'll just highlight a couple. He's a fellow of the American Academy of Arts and Sciences. The parent organization for many of us in the room here, the AICHE, has recognized his work with 2 institute-level awards, the Colburn Award as well as the Wilhelm Award, and a division award, the Cass Division Computing and Chemical Engineering Award. Yannis started his career at Princeton in 1986 in the Department of Chemical and Biological Engineering as a faculty member. Over the course of the years, he's held visiting professorships at Wisconsin, Patras, Colorado, Caltech, and Dortmund. And so one addendum to the bio is, through the courtesy of social media, I happened to trip across a very interesting announcement in Facebook late yesterday, which is that Yannis will be moving geographically a little south of Princeton, New Jersey, to join Johns Hopkins University, where he will have a joint appointment in engineering as well as at the medical school. So as we welcome Yannis, let's congratulate him on his new appointment.
What really happened was that George said he would retire, and then I said I have to do the same thing. So I am retiring from Princeton and moving. So until I heard Manfred this morning, I thought that I was going to try and tell you funny things about no equations, no variables, and no parameters and all that. And I kind of now realize that all I'm going to tell you is about choosing the right input-output decomposition. So this is very much the same thing that you heard before. So this was 1980. And I don't know why, but the slides, here they are. So this is where George found me, or where I found him. One of the wonderful Minnesota jokes is, with apologies, Shirley, congratulate me, I hired Jesus Christ. So this is why, and you see he looked even more than that in the picture that Manfred had. And what he did is that he sent me to Minneapolis, and to Scriven and Aris and Lani, who is doing great. And I remember him telling us, in Minnesota, you will not just become engineers, you will become scientists, you will grow wings. And the time that we had the first Scriven exam, it was a freezing rain outside, and it was difficult to walk to the department. I remember Andreas Budovi saying, man, these wings would be really helpful now. So George has always been, from back then, and through his career, a window for many of us, a window to the US at the beginning, a window to technology, a window to the future, a window to new ideas. I still remember, I wrote to him earlier this year, I remember him telling us in the design class in Athens, and you know, in the States, there is this thing that I saw. It is possible to touch a screen with a stylus, and it actually can give input to the computer. And this was 1980. And well, today is another one of these windows, these 2 days, and I look forward to the next windows. What I really want to talk to you then, let me kind of say it again. I'm really going to tell you about just choosing good variables with the help of machine learning, good input-output, good observables for dynamical systems. For many years, I've kind of tried to work without equations. This is a little demo of this. This is a complex system. It has 20,000 little particles. Each one of them is supposed to be a plankton microorganism. They live on the surface of the ocean. They give birth, they die, they swim around, they're being swished around by the ocean. And what you see is two views of the same thing. On the left, you see the messy thing. That's the 20,000 particles. On the right, you see the right statistics. It's the pair correlation function, how many friends they have in their neighborhood. The important thing being that on the left, you see something horrible that goes around, has striations, never dies. And on the right, you just see a first-order system that has a transient to a steady state, maybe with a little bit of noise. So the important thing then is how a lot of our education goes into how do we observe the thing on the left to get a nice equation for the thing on the right. And equation free is just, if I have an algorithm, if you think about it, the algorithm never actually sees the functional form of the equations. Any algorithm, like an integration, the algorithm gives x to the subroutine, and the subroutine gives you back f of x, dx dt. So all the calculations are done without the functional form. The one case where you need the functional form is when you do underestimators in global optimization. But in almost everything else, you don't really need to see what the equation is. So you can write an algorithm which, instead of using an equation for the pair correlation function, takes an initial condition, makes it particles, run the particles a little bit, observes the particles and estimates the time derivative, and then uses this to make a step. So in effect, you're integrating the equation without writing it down. And it is clear that this is very much a realization problem, an estimation problem, an input-output control problem, only that the system, the plant, is the microscopic calculation that you can put in your pocket or that your algorithm can keep in its pocket and run it on demand and estimate what it wants from it. So this is very much input-output stuff, but it's input-output for computational experiments, not input-output for experimental experiments. And for many years, we've worked on this, and you can do no equations, meaning you can solve the equations without writing them down. The main idea is that you have your plant, and that's a detailed simulator, and somebody tells you what the right variables are, and then you can use just the idea that the macroequation exists to solve the equation without writing it down, without getting constitutive equations. You get them on the fly. But the big thing that I realized as time went on is that this is relatively easy. What is much more difficult is knowing what to observe. If you look at a messy system and it's not one that is already in your books, and you don't already know that the right thing for kinetics is concentration and temperature, and the right thing for Navier-Stokes is momentum and density or something like that, if you look at a new messy problem, how do you know what are the right variables with which to observe it, with which to write a model? And so this is kind of my childish example. This is two pendula that are kind of running around. You look at this little movie, you say there's masses, there's lengths, there is a spring between the two pendula. You know that there exist normal modes, they can oscillate together or against each other. And here is an example where the parameters in the problem are are time dependent. You see the spring is kind of getting stiffer and stiffer, and as it oscillates, the oscillations get faster and faster. And so what I want you to think now is exactly the same picture, but if you look, there is like gradations, there is 10 by 10 pixels. So what you do is that for every snapshot of this movie, you take these pixels, you mix them around, you calculate the average color intensity in each one of them, and then you multiply it by a random number. So what you see here is a snapshot of the previous movie. Only this snapshot, it's one-to-one with the previous movie. Everything that I'm going is everything I'm doing is invertible. However, this makes no human obvious sense. And if you run this, then what you're going to see is that, well, you can see the pendula oscillating. I hope you can kind of see that as time goes on, things go faster and faster. The flickering gets faster and faster. I don't know if this is visible. This is as much as I can kind of tell you to convince you that what you're seeing is the previous movie. And the whole point of the little thing that I want to tell you is that if you do the spectrogram of this, so if you do observables of the problem, then the observables that you get from the messy thing and the observables that you get from the physical thing, you see the red is the constant frequency of the oscillation, and the yellow is the time-dependent frequency. That is just one set of observables. The basic point is whether you're looking at the system through variables that make sense humanly, or whether you look at systems through variables that are nonlinear transformations of the variables in the problem, it makes no difference in principle for the computer. So the main idea is that to be predictive, we often use human observables that make sense to us and write models for these laws that we understand. But even if the observables are not the usual ones, but functions, invertible functions of the usual ones, and that's very common, as we heard, in control practice, then we could be predictive in terms of incomprehensible observables, and we could write very predictive, incomprehensible humanly laws. And sometimes then you think, well, even in the problems that we actually do know how to model, who said that the observables that we usually have are really the best ones? Maybe there is better incarnations of the equations that we know and love. And so what I want to talk about today a little bit is looking at data-driven intrinsic observables. Don't worry about the Mahalanobis diffusion maps. Where do good observables come from? Sometimes they come from some systematic hierarchy, like you have monomials, you have several terms in Fourier series. Sometimes they come from somebody being wise, knowing a lot about the system for a long time. The thing that I like to say is that all of us, most of us have our retirement fund in some money in some fund, and there is a person that reads the market and decides what to do, which means that they have a model in their head. And is this a good model? Do they even exactly know what it is that they are observing? There is a lovely paper that is called Reconcilable Differences from Oliver Wyman, where somebody showed that 3 different companies had completely different measurements, completely different optimization functions, but they resulted in exactly the same buying policy. The paper was called Reconcilable Differences. Obviously, they were observing different observations of the same thing. And so the main thing that I want to say, which is machine learning today, or one option of machine learning today, not very different than the shallow networks, if you want, from the 80s, is that we can use data mining and manifold learning techniques in order to learn the right observables with which to observe messy systems so that we can be predictive about them. My particular poison is diffusion maps, but it does not matter. You can think of kernel principal components, you can think of isomap, you can think of many other things. It is the nonlinear incarnation of principal components that started becoming popular around 2000. So this is my little example. This is my attempt at becoming a little of a computer scientist. This is a particular bifurcation. It doesn't particularly matter. Dakens-Bogdanov is what happens when two things go wrong at the same time. You can think that you married the wrong person and your mother-in-law doesn't like you. Two things are bad at the same time. When I first said this, I was told that maybe this means subliminally something about my family life. So now I say, your car, you hit a pothole and the radiator explodes at the same time. So this happens here. There is 2 zero eigenvalues at the same time. And we kind of know that in the neighborhood of this, there are all of these phase portraits. And it turns out that there is something that's called the normal form for this. It's a system that has 2 state variables, x and y, 2 parameters, 2 equations, and every problem in the world that has 2 things going wrong at the same time can be mapped 1-to-1 to this system. This is a normal form. But this is just an example. I want you to think that I have a system that has some state variables x, some parameters p, some evolution equations f, some observation function g, and I know absolutely nothing of all of this. The only thing that I know is that I have a whole bunch of experiments, trials. That is, I set the conditions. I don't know what the conditions are. I just set the conditions, and then I get a whole lot of measurements out of the problem. And so this is more input-output stuff, and maybe it's worth kind of saying that Kalman passed away last year. And this is another amazing guy. You can tell it's 1981 from the hair. He did this paper, which I think of as a small miracle, and then he didn't really do very much after that, and I've been trying to find him. What he did is that he did input-output balanced realizations for linear systems. That is, give me the inputs that go into a system, give me the outputs, and I am going to come up with a minimal and in some sense robust realization of what the system does. I'm going to give you equations which with these inputs give you these outputs. The main tool at the time was singular value decomposition, and as you kind of all control people know, this came from aligning the observability and controllability subspaces. And this is now done non-linearly. So this is my parameter space. I have no idea what my parameters are. This is a blind monkey. The blind monkey turns a knob, and there is a dart that is thrown somewhere in parameter space. I fall in blue conditions, and then for the blue conditions, I get 500 short time series. I measure 500 channels. In everything that I'm going to tell you, I have plenty of measurements. I don't know what I am measuring, but I have plenty of measurements. I'm not trying to get away by having a small number of data. So for the blue conditions, I make blue measurements, and for the yellow conditions, I make yellow measurements, and for the green conditions, I make green measurements. I have no idea what the conditions are. I have no idea what it is that I'm measuring, but it's enough. And so I only really have labels. I know that there is experiment 19, experiment 25, and for each experiment, I have channel 1, channel 2, channel 500 measurements. In effect, it's like I have a whole bunch, like let's say 100 experiments times 500 measurements. I have 50,000 hairs, and the only thing that I know is that blue goes with blue and red goes with red, but I really don't even know that. I just know that there is some hairs that come from experiment 19 and some that come from experiment 25. And so here comes the data mining. Let's see if I can do this well. I take all the hairs from all the experiments, and then I do data mining on all of these hairs without taking into account what experiment they come from. Here is a way of thinking about it. You get 500 people from Stockholm, 500 people from Tokyo, since George went there, 500 people from Cairo, 500 people from Zurich, since Manfred came from there. And what I do first is that I look at all of the people. Let's say that the hairs, it has to do with whether they're straight or curly and whether they're going left or right. So think of this. From Stockholm, there's going to be a lot of tall blonde people. And let's say from Cairo, there's going to be, let's say, Athens, so that I don't offend anybody. From Athens, there is a lot of shorter, darker people. When I look at all the people that are tall and blonde, many of them, the blue, will be from Stockholm, but there will be a few from Athens and Cairo. If I look at all the curly hair people with dark hair, then there will be somebody from Stockholm, but a lot of people from Cairo. So the main idea is that when I do this data mining, I find a way of comparing all the trials, And now that I have a way of comparing all the trials, all the measurements, I take all the people from Stockholm and all the people from Cairo, and then I do an Earth mover distance. That is, I find a way of calculating the distance between all the time series from experiment 19 and all the time series from experiment 29. That will give me a sense of how far experiment 19 is from experiment 29. And so now, next time that I'm going to compare two tall, blonde people, I will not only look whether they look the same, but they'll have some extra information that tells you, are you coming from an experiment that is close to the experiment of the other guy? Or are you coming from an experiment that is far away from the experiment of the other guy? You can think of this process as giving a little color to the hair. That is, first you look at them without wondering about what experiment they come from, and then you compare the experiments, then you recompare the trials based on the information from the experiments, then you get a new geometry for the experiments. I know that I'm not doing a very good job, but what I'm trying to tell you is that you iterate back and forth between looking at the individual measurements and then looking at the ensembles of measurements. And by going back and forth between the two, what you get in the end is that you can get back the parameter space. So this doesn't look very impressive. I was very much impressed when the postdoc brought it one morning. This is the parameter space of the original system. This is 400 different experiments. These are settings of the parameter values. What you do is that you choose the parameter values, but you label them, and then you hide what the parameter values were. So you just have from 1 to 400. And then for each one of them, you do experiments, and you get a lot of time series, but you mix up the time series. You don't know what initial conditions they come from. And then you do this data mining magic. And then what happens is that the thing comes back and tells you, you know, really, these 400 experiments that you did, they really are a two-parameter family of experiments, and they should be organized this way geometrically. And then you peel off the little white paper with the label and find that the blues are close to the blues, and the purples are close to the purples, and the greens are close to the greens. And so what the system does, it doesn't give you the actual parameters, but it gives you a realization of the parameters. And if you look at this carefully, you will see that not only is it homomorphic, but it is isometric. And then it tells you, you know, you had 500 channels. Your 500 channels are really a two-parameter family of channels, and you should plot them this way about who is the neighbor of whom. And now you see that these are the realization of the state space that comes from the data mining, and they are colored by the original X and the original Y, from which I want you to kind of see that the realization of the phase space that you get from the data mining is a slight rotation and deformation of the true phase space. You understand, it has no way of finding the true phase space. It can only find a realization of the rate space, of the phase space that is minimal, and in some sense as simple, as robust, if you want. And the thing that's the most amazing of all is that if I now pick a hair, I know a realization of its parameter values, I know a realization of its state space initial conditions, and I know a time derivative, which means I have a tabulated equation out of knowing nothing, but having enough data. And so the most amazing then thing is that it is possible to get the normal form of a given behavior. And I'm going to also say, and maybe not stress this very much, that if you have two different systems that have the same normal form, then by doing data on the one and data on the other, you're also going to realize that they're really the same system, that they are directly mappable to each other, which is kind of the ultimate pre-computation. If you know what happens in the normal form and you learn the mapping between the system and the normal form, then you know everything in advance. In what I told you so far, I told you about no equations first, and then I told you no variables and no parameters. And now I want to kind of joke a little bit and talk about no space and no time. So in 1979, the Americans, I should say we Americans, I am also now American, left the embassy in Tehran. And I don't know how many of you saw Argo. And because they didn't expect they would have to do it, they didn't have time to burn the documents. And so what they did is that they shredded them. And then what the Iranians did, or at least what Wikipedia says, is that they took skilled carpet weavers and they closed them in a room and said you cannot get out until you kind of put the secret papers back again, string by string. And so here is a secret paper. This is the output of a partial differential equation. This is space, this is time. Think of this as a concentration pattern in a tubular reactor. And what you do is that you go and shred all of this piece of paper, which means that what you get is 200 time series, okay? No, actually 512 time series. And what I do here is that I shuffle them all together. So I kind of don't know where each of the time series came from. Well, it is very, very easy to do data mining and get the original page together again. What is the basic idea? It's the same way that you would solve a puzzle, or your kids and grandkids solve puzzles. You think of each one of these time series as one puzzle piece. Then what you do is that you compare them all in pairs and find who is the nearest neighbor to you, and then where is the next nearest neighbor. It's just that it is very nice to do it through an optimization problem, in particular through an eigenproblem. And so this says if you somehow lost your time measurements, you could reconstruct them. This is the same thing, but in 2 dimensions. This is one space dimension, another space dimension, and time. You take this and you push it through a meat grinding machine, and so it's going to give you 200 by 200 strings. You do data mining on these 40,000 strings, and what you get is something that is, you understand, it cannot be the original space. It is going to be a homeomorphism. It is going to be a realization of the original space. So in what I told you first, not only variables, but maybe also space can be reconstructed from data. And I wanted to give you at least one example that is more research and just ideas. So here is 512 neurons. This has something to do with a suprachiasmatic nucleus, in which we have a grant with Mike Henson and Eric Herzog. And the basic idea is that you look at all of these guys, and these guys are all heterogeneous. They're heterogeneous because their kinetics are heterogeneous. They're heterogeneous because the degree of the connectivity in the network that they are is heterogeneous. And then you do a lot of data mining, and what you find is that, gee, this is really a 2-parameter family of neurons, and you can actually create a space. You see, this is a network. There is no physical space. You can create an embedding space for them that makes sense. And if you color this space by one of the kinetic constants and by the degree, you find that they are 1-to-1, which basically is telling you that you can think of this network as an embedding, as a partial differential equation. Only instead of it being a partial differential equation in x and y, it is a partial differential equation in the kinetic parameter and the degree distribution and the degree of every node in the network. That is, you can create a space in which it would make sense to observe this as a simpler problem. The same thing can be done in time. Before, what I did is that I shredded vertically and I got space out of the measurements. This is shredding horizontally, and then I can get time. So this tells you if you get a movie and snip, 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 you take scissors and you cut it, then you can very easily put it together again. And there's nothing special about space or time. You can take this movie and take a cookie cutter and chop, chop, kind of break it into a bunch of little squares, and it is a puzzle, and it's exactly the same algorithm that our brain does when it solves a puzzle. You can put it together again. And for fun, this is Germany. This is work done with a bunch of German collaborators, and this is a shredding of the geography of Germany. What you do is that you go on a given day in Germany, and you look at each one of these cities, and you create a Boolean vector that has darkness and light. And you look at all of these vectors, and you do what I already told you before, and what you get is Germany back. You don't get exactly Germany. You get something that is homeomorphic to Germany. But the thing that is more important, and that's kind of the last thing that I want to tell you, is that in what I showed you, I do one kind of measurement. I look at daylight time one day of the year. Here, I do a different kind of measurement. For every city, I go and look at 2 numbers on every day of the year. One number is when it was sunset, and sun up and sunset. And if you do data mining on these data, then you get back the same Germany. And basically what I want to tell you is that it is also possible to have extremely heterogeneous measurements of something, but as long as you do your data mining the right way, then you're going to get the same embedding. That is, you're going to understand that it's exactly the same problem. This is what the physicists call gauge invariance. Gauge invariance means that you're understanding something independent of what the instrument is with which you're measuring it. There is something funny in this. Of course, you cannot have a crazy instrument to measure temperature, but as long as you're measuring something which is one-to-one with the thing that you want to measure, then you can reconstruct the correct, if you want, normal form. So you can understand your problem, and you can be predictive about your problem, even if you don't use the same measurements that you would normally use to understand and write models with. As long as you have generic observers is the appropriate word, as long as you measure things that have a reasonable derivative with the things you want to measure, and you measure enough things, you can be equally predictive, which is very medieval. It means that you can be predictive without really understanding what it is that you are observing. This is my attempt at being funny. This is, I don't know, you can say this is, we're in Boston. This is Boston on a summer evening, and you look around in Boston, and there is a lot of people. You look at these 4 windows. You kind of find that there is these people there, and they all look different. They do very different things. But if you went to, what's the analog of Carnegie Hall here? If you went to the Boston Symphony, you can't hear the sound very well, but you would see that this guy, Levine, and Marta Argerich, and the other guys, they are musicians, and they play together in an orchestra. The main point in this is that your neighbor is not necessarily the one that is next to you, but that your neighbor is the guy who is doing the same things that you do. And so what I'm going to kind of close with is a movie to give you an idea. This is a partial differential equation in space and time. These are 2 very different ways of looking at it. This is the usual way that we look at it. We look at behavior as a function of space and time. This is, if you want, one of the concentrations that are taking part in this reaction diffusion problem. If you play this, what you're going to find is that there is horrible spatiotemporal stuff happening down here. But if you look at the colors have been chosen by data mining so that things that have comparable color are kind of doing the same thing. It's as if this was an assembly of heterogeneous cells. The cells that are blue now are doing the same thing now. They're dividing. The cells that are red now are doing the same thing now. They're growing. And what I want to show you just as an idea is a different realization of the same process. Here, instead of looking at where activities are in space, so instead of observing the problem in physical space, I observe it in activity space. And this thing that flies over activity space is how many cells are doing blue now? How many cells are doing yellow now? How many cells are doing red now? And if I play this again, you will kind of see that what was really horrible and spatiotemporally chaotic on this side looks very much like a supply chain here, something almost periodic. Something happens, and then the next thing happens, and then the next thing happens. The main idea, again, is that maybe physical space is not the right way of observing things. Maybe there is better embeddings in which we can write better models. So I've kind of run over. The main thing that I told you, I appreciate that this is both funny and a little ridiculous and a lot medieval, but the basic idea is that it looks as if instead of putting our intelligence in understanding physically what it is that we're doing, we seem to be starting to put more and more our intelligence in the data mining algorithms that will do the predictions by going directly on data. And that's something that a lot of us do. Let me also say there is a good friend, Alex Mitsos, who I'm not going to say this. I'll just say something that he asked me to say for George. So this is George as an oracle. It says, Professor Stephanopoulos has given me plenty of advice, which was always crystal clear and in retrospect correct, which is good. And then this is something that I will say in Greek for him. You already saw this picture. I am fond of this little, not important poem. It says, «Σοφέ μου το τετράσοφο που σε φωτάει λιχνάρι, να ήταν λέει φεγγάρι και εσύ 20 χρονών, χυλάκια ανθούν στη γειτονιά, γαρίφαλα στη γλάστρα, μα εσύ διαβάζεις τα άστρα και το βαθύ ουρανό». So, thank you, George.
Thank you, Giannis, for a magnificent talk. If there are any questions in the audience, could I have you come down to one of the microphones to address your questions so we can all hear? Venkat.
Nice talk, Giannis. Quick question. In physics, the gauge invariant property comes from underlying symmetries of the equation. So what would be the corresponding symmetries in the kind of problems you're studying?
It is the symmetry to all diffeomorphisms, which is all different invertible functions of the same observation. Think of it, you have a function, and then you think of every function that is 1-to-1 over this. So this is a very much richer symmetry than translational invariance or scale invariance or whatever, and that is the appropriate symmetry. The appropriate symmetry is, as I told you, things that can be transformed to what you want invertibly. Okay?
Okay, thank you.
Is there another question in the audience? If not, maybe I'll take liberty and ask you one. Oh,
Yeah,
there is.
go ahead.
Perfect.
Is invertibility a necessary condition or something that can be relaxed in your
If you would like to ask me what my major dreams are, the easiest thing, by the way, let me say that all I said is calibration. When you have a thermocouple, the thermocouple does not measure temperature. It measures something that is 1-to-1 with temperature, and you have a calibration curve that brings you down to curvature, to temperature. All I told you is look at things that can be calibrated back to what you do smoothly. If you ask me what my major dreams are what if we can go beyond invertible transformations, but also think of singular transformations. So what if we also had bad mirrors? What I've been telling you is looking at things through funhouse mirrors, if you want. Instead of looking at me, you can look at a thinner, less white hair, better looking, smarter version of me and still think that it is me. I should also say, the last thing that I will say as I walk out is that when George came the first time in that class, he looked very young and he looked a little bit like Jesus Christ, and he had jeans and I don't remember if it was a shirt or a t-shirt. And at the time, you must realize that all the professors were kind of like I am now, old, white-haired, portly, with a tie. And we were wondering, who is this kid kind of down there in the class? He always has this sense of being a kid down there in the class, even when he is very important and with all the gravitas and everything. Thank you again, George.
All right, our next speaker has a couple of connections to George. One is through the family tree. Kostas Pantelidis is actually the uncle of George through the Roger Sargent family tree. The second connection one might think of as a near miss. So in 1981, Kostas got his undergraduate degree in chemical engineering from Imperial. And in 1985, he got his PhD from Imperial. But in between, in 1983, he got his master's in chemical engineering here at MIT. And if you remember Paula's introduction, George arrived at MIT in 1984. So George tells me he's never forgiven himself for not having the good sort of insight to arrive a year or two earlier to MIT and have the opportunity then to overlap with Kostas. So Kostas today is a faculty member at Imperial College. He is also the CEO and managing director of PSE Limited. Many of you know PSE Limited is one of the world's leading providers of model-based innovation services and advanced process modeling software. He has published over 100 articles in the PSE literature. His work has been recognized by a number of awards, and as I've done before, I'll just cherry pick a couple of them. In 1998, he received the prestigious Bilby Medal and Prize, which was awarded jointly by the United Kingdom Society of Chemical Industry, the Royal Society of Chemistry, and the Institute of Materials. More recently, in 2015, he was recognized with the Roger Sargent Medal, another top honor in our field. So I'd like to invite Kostas to come up for his lecture.
Thank you, Frank. As Manfred mentioned, it is very difficult to predict the future. I have to say I admire from Manfred the way you deftly avoided making any predictions. I took my remit a bit more literally. which is I found extremely difficult to put together this presentation, although it's only a short presentation. So instead of putting the slides together, I started thinking, how far back do I know George? When was the first time I met George? And actually, it was 32 years and 2 months ago. It was PSE 85 in Cambridge. There was a presentation by Jeff Barton of the University of Sydney. So it was about control system synthesis. Jeff finished his presentation, and the chair of the session asked, any questions? Professor Stephanopoulos. So you asked the question, and then Jeff started laughing instead of answering the question. He pulled out of his pocket a piece of paper and said, this morning, I received this fax from my student in Sydney. It says, and I hope George Stephanopoulos asks you a really difficult question. And it just dawned on me at that point that actually this is what you have done to us on this occasion. That consistently over the last 40 years, you've been asking very difficult questions. And as one additional contribution, you pose this question of what's going to happen by 2040. Now, 2040 is 23 years from now. If I go back 23 years, 1994, could I predict in 1994 what would be happening in process modeling or indeed anything else? By now, the answer is definitely not. I got everything wrong, I predicted. But here's my chance to make a fool of myself once again. Okay, so thanks for organizing this symposium, in this occasion. And I'd like to tell you what I think is going to happen. Before I do that, very briefly, I want to say, where are we now? And I only have 4 slides to summarize where we are now, which is really not enough. As I said, I will make a fool of myself by trying to make 3 predictions as to things which might happen, which make a big change in the way process modeling is being done, and just conclude. So where are we now? Basically, I've been doing modeling for, 35 years now. I always find it very useful to think of modeling along 3 directions, because this is what allows you to determine where you are and whether any progress is being made and so on. One note here, those of you who were in the FOCAPO CPC conference earlier this year will have seen some of these slides before. I have to assure you, it's only these 3 slides that are the same. Okay, so do not despair just yet. But basically, when you try to position any kind of process modeling or process modeling technology, it really helps to look at it in along 3 axes. The first question you have to ask yourself is, what part of the universe is this model trying to describe? Is it trying to describe a single molecule, a single particle of catalyst, a certain tube of heat exchanger, a piece of equipment, all the way to supply chain? That's the system scope. The second axis, of course, is a system is made out of components, of the units in this system, and indeed, what kind of physical detail goes in each one of those components? Is it a sort of lumped unit? Is it 1-dimensional, 2-dimensional units? Is it 3 or 4-dimensional models, and so on, of the kinds that are being used nowadays? And the third question is, and what do we hope to do with this model? Okay? And this is where we look at it along the traditional axis of process development, the process life cycle, all the way from early stage conceptual design, when we design the catalyst and the basic equipment, to the front-end engineering design, to the detail engineering, to operations, automation, and control of the kinds of things that Manfred was talking about. So if you want to see what progress means and so on, you really have to see, or it helps, I think, you don't have to, but it helps to look at it in this context here. And if you look at what's happening nowadays in terms of the drivers, basically we're pulling ourselves into considering bigger and bigger systems. The reason for that is quite simple, that when you're trying to optimize a system, you have to make sure that anything which is being optimized is within, or all the interactions are within this envelope. Otherwise, you're just fooling yourself that you're really optimizing the system. It's meaningless to optimize a single unit operation, or indeed, as increasingly we find out, a single plant, and I'll show what that means in a second. The other dimension is there, and indeed the question is not quite why or what you're optimizing, but why whether you can trust the answer. And people are increasingly realizing that there's a limit of complexity below which, a limit of detail below which this whole modeling thing is meaningless. You can solve the optimization problem, you won't believe the answer, or you will have to do all sorts of ad hoc adjustments to that answer. At that point, you've just wasted your time. So increasingly, what they're looking for is putting more and more physical detail so that when we optimize the system here, we believe the answer, okay? And finally, of course, these models do not actually come very cheap once you have a very large system with a very detailed model down there. So really what you're looking for is leveraging, which is a just polite way of saying, make sure that once you make the investment here, you can use it along the entire axis there, okay? So we are looking for models which can be used, despite their complexity, along these two axes, which can be used as far down the chain here as possible. And one of the biggest developments in recent years, one of the things that we are very keen on, is how to take models based on first principles all the way to real-time operations and control and so on. And that is something which is a developing situation. I'm not going to put that in the future because I think it's something which we will see more of in the next 5 to 10 years. But anyway, this is where we are. And just as a final part of this introduction of where we are, this is the case study I presented in January, which is something published by Shell towards the end of last year, where they're trying to optimize the entire production of gas production and processing in Iraq. Okay? So this is a model which, or this is a system, not a model, forget a model, which comprises a number of oil fields, it comprises a number of plants, NGL plants, LPG plants, it comprises a number of sources and, sinks and consumers and so on. And this is the kind of thing which in the past would be done using a supply chain model. Shell and other companies like this have been doing this for 40 years. There's nothing new in putting a model like this, which represents the entire network and optimizes it. And this is, just some of the details of the plans and so on. Now, the real difference in what was published in last year is that instead of using very, very simple linear models of the kind that is normally used for supply chain and strategic planning, here we're using models which are comparable to the kinds of models we would use for single plant optimization, okay? And I don't go into the details. Now, what do you get in this case here? You get a model with 300,000 equations, so I'm afraid, Yanni, we're back to equations here. 300,000 equations, and you optimize it. Whether you optimize it as a single system or using some kind of decomposition or whatever, I mean, that is a detail. The key issue is the model formulation and the data going in it. And why would you want to do this? Well, for that reason there. Basically, you can show you get about 5% improvement over a simple situation. You're using simple models, which you then have to bag off constraints and so on. And on a system like this, we're talking more than $100 million a year in that improvement. So this is more or less where we are now. In the very traditional area like this, we can do pretty much everything. The technology is evolving and so on. Now, before we pat ourselves on the back, we have to realize these are the promises the process systems engineering community have been making to industry for at least 20 years, maybe 30 and 40. Yeah? I can remember myself, not going very far, making promises that one day we'll be able to do this kind of thing. Well, this day is here and so on, but now we have to look forward. So this is really the rest of the talk here. Where do we go from here? So there are many, many things we can do. I had to pick 3, because it's only a 20-minute talk and so on, okay? So where can we make the biggest impact? And really, the first one is we have to look at why isn't this brilliant kind of technology, we are where we are now, we can solve absolutely everything, why is it not used everywhere? Why are we still having so much resistance in applying modeling to these things? And one of those things is the cost. It really does cost a lot to build a model like this, and indeed to use it in a model-based engineering project, which starts with the business objectives and delivers the business deliverables. It starts with the objective of let's optimize the operation, the day-to-day operation of the entire Iraqi gas production, and then it comes up with a system which day in, day out tells you this is what you should be doing. You should be sending the gas today. You should be sending more gas this way and less gas this way. You should be selling this. You should be buying this. You should be doing this kind of thing. It's very simple. Now, I've had the benefit, and unfortunately, this kind of information is not really available very easily to academic researchers, but because of my sort of more commercial association, I had the benefit of looking at many of these projects and to sort of look at the analysis of where the time goes in doing, or the effort goes in something like this. Obviously, you have to formulate your objectives. You have to decide what modeling approach you're going to follow. You have to build that model. You have to make sure it's correct. You have to validate the model. We'll come back to this. And then you do some calculations here. And of course, very often you find that you have to go back and revise your objectives in terms of what is achievable, or maybe the model in terms of what you find out here, and so on. But these are the important numbers here. So if we look at a conventional sort of, traditional industry process modeling project nowadays. This is where the time and the effort goes, okay? What we find here is that actually very little time goes there. Some time goes towards constructing the model and making sure it's correct. And a lot of time goes into this model validation, really making sure that the model reflects the physical reality. And then actually, interestingly, very little time is left, to be honest, by that time, to actually use the model and get something useful out of it and deploy the application. Now, if we want to increase efficiency, this is what we need to target, okay? Now, looking at what's happening more recently, there have been a lot of developments in modeling technology in terms of putting together very complex models, solving them, not getting stuck with minor things like convergence failures and so on. So actually, that bit here is coming down, and that bit is reaching about 75%. So if you ask me off the top of my head, we're going to do a project, it's going to be 6 months. How long are we going to spend on experiments and validating the model? That's going to be 4 of the 6 months or 5 or 6 months or something like this, okay? So this is where really we need to focus. And of course, if you follow a system approach where the system is made up of components, really most of the possible errors are coming from the models of the individual components. And then if we look at the models of the individual components, really what they're looking for is the characterization of the physical phenomena which appear in those components. Okay? So we're not talking about something very vague, we're talking about some very specific things: thermodynamics, heat mass transfer, hydrodynamics, in particular, the kinetic phenomena like reaction and kinetics. Now, typically, and the reason why it takes so long with experimentation, which is very expensive and so on, is that the only way we have, or the main way we have nowadays for getting this data is by estimation from experimental data. Sorry, getting these parameters we need from here, the characterization of the physical phenomena, is by fitting experimental data, and this really is where the bottleneck is. Now, there are well-established ways of doing this in a very systematic way. We're much more systematic nowadays than we used to be in terms of performing some experiments, fitting parameters, assessing the accuracy of those parameters using some very crude, I should say, I'll come back to this, statistical measures, coming back, designing more experiments and going round like this until we do this. But this is where those 4 out of 6 months go. This is the biggest obstacle to applying model-based technologies to a much wider range of applications. So what's the alternative? Really, what we're looking for and where the big benefit may come in the next decade or two is from multi-scale modeling. Again, multi-scale modeling means everything to, or many things to many different people. Really what we're looking for is particularly in terms of the characterization of the basic behavior of materials, okay? We're looking at things like the use of molecular modeling or quantum mechanical modeling for thermodynamic parameters, for example, thermodynamic behavior, the use of computational fluid dynamics for extracting hydrodynamic parameters, and so on. So this is where, if we make a breakthrough, we're going to eliminate a very large part of the entire effort it takes to apply modeling to any particular situation. Now, what's new about this? Nothing. I mean, many people, including myself, have been talking about multi-scale modeling for decades now. Okay, it's a very old new paradigm. So what are really the challenges for this? Well, the challenge for this is that really this thing doesn't yet deliver what it's meant to deliver. And there are really 3 challenges there. The first thing is whether there are multi-scale modeling approaches for describing the particular phenomena of interest. Okay, if I'm interested in crystal growth, can I build multi-scale models or fine-scale models, physical chemistry models, for describing those things? And the answer most of the time is yes, someone has already done it. It's the second point, which is actually more important. It's the accuracy of that prediction. In process modeling, we're way past the point when the purpose of computation is to provide insight. Yes, it's very good to get insight, but really nowadays we're much more demanding. We are looking for predictive accuracy, very often in continuous processes of the order of 0.1 to 1%. So to say we've got a fine-scale model which predicts, let's say, the thermodynamic behavior of a certain material or the kinetic behavior of a certain material in very qualitative terms, it's very nice that we have it, but we cannot use it in this. We will always go back to experiments in that case. So this is where we need a step change in capability and so on. And then, of course, once we have these fine-scale models, there is a question of multi-scale integration. Yanis didn't say much about this, but many of the techniques that he was alluding to are actually process systems engineering techniques for achieving this. So the main contribution of process systems engineering methodologies are actually down here in delivering this kind of integration. Now, the more interesting thing, and actually the area where I do most of my research, whatever that is left of that at Imperial, is actually up there. That these are all problems, for example, usually in physical chemistry. But I do believe they can benefit from some of the process systems engineering thinking in terms of setting objectives which need to be met in terms of accuracy and efficiency, but also in terms of the underlying mathematical analysis and so on. And this is what we've been trying to do at Imperial with some of our work. So let's give you two examples, one which works and one which doesn't yet work. So here's an example of multi-scale modeling, where we start with molecular interactions in the fluid phase in terms of functional group decompositions of the molecules. Those are described to a fairly high degree of detail. They go through the statistical thermodynamics machinery, and you end up with what might be called an equation of state, but it's actually orders of magnitude more complex than a cubic equation of state. This is a situation where now we have got to the point where we have a single thermodynamic model which can predict pretty much, well, it's very difficult to say all, but a huge variety of systems. And I insist on the word prediction. Prediction doesn't mean give me some experimental data and I will fit it. You can do this with Payne-Robinson. Yeah? It really does mean prediction. You can take a molecule you haven't seen before and actually predict. And when you compare with experiments, yeah, it's fairly accurate. So that's a good news, or a good example. Here's another situation, which is not yet at that stage. So that was fluid phase behavior. This is a fluid solid behavior, prediction of solubility for the purposes of process modeling. You know, people do crystallization modeling and so on. This is the kind of thing they need. There is a route which is based on ab initio crystal structure prediction. We can take a molecule like this, which is molecule 26 from last year's or 2 years ago blind test. We can predict the lattice energy landscape. We can pick, indeed, without any human intervention at all, based on quantum mechanics only, we can find the most stable polymorphs. Okay? The theory is, from that point onwards, we need to be able to predict the free energy landscape, and from that we can predict solubility using standard relations. So this is something which would, if it worked, it would eliminate a huge amount of of the effort required in any project to have crystallization or whatever. The problem is, we have a big hole in the middle there, where our ability to predict free energy landscapes is still quite limited in terms of the size of molecules like this and so on. So we are struggling a bit here. But this is where any breakthrough in this kind of area would immediately translate into a major improvement in process modeling. The second area where perhaps we can see a big development, in my opinion, is when process modeling goes beyond manufacturing, okay? So really, it's about the scope of the system here. Say we go all the way to supply chain, but actually this is all about manufacturing the product and selling it and so on. And really what we're looking for is the product function. The example I want to discuss with you is in pharmaceutical systems. Okay, so in pharmaceutical systems, where of course, as people who are involved in this area know, we have the manufacturing of the active ingredient and the manufacturing of the product, the tablet or the capsule. And these are very well defined chemical engineering problems, process engineering problems. There's nothing new to say there. Like in any system, the systems approach is what are the inputs, what are the decisions at your disposal, and what are the things you care about. You build a model, you integrate the model, you optimize. Except that in the case of pharmaceuticals, what you really care about is not represented by any of this. What determines your future, which is the FDA approval, is not whether you have the right purity or whatever. It's whether you have the right biological performance. So really what matters in pharmaceuticals is what happens when you take this tablet and the patient swallows the tablet, then it dissolves, it goes to the intestine, it dissolves, it permeates into the systemic circulation, and then it achieves hopefully, the desired biological effect there. So what we have here is a system where the things we can manipulate as engineers are over there, but the things which really determine success or failure are over here. The obvious approach there, the obvious conclusion to this is you need to take a system envelope which encompasses the biology, okay? not only to study this in terms of models, but actually to have an integrated system model like this, okay? So really, the idea here is that we use an integrated system model to quantify the effects of the red things or the blue things, and this is really what is driving or would drive the efficiency of new drug development, if not discovery. It's not entirely a dream. We have begun to do work like this. This is a tool we've been putting together in PSE called Gibbons Formula Products. It's a vision we are trying to realize in collaboration with some of the major pharmaceutical companies. But this is very early days. Really, to achieve this, we need to make a lot of innovations in terms of system technology. For example, if we look at this, even some mundane thing like the description of the material going from one unit to the next, you might think it's just a simple flow sheet, but here we have an amorphous fluid. Here we have some crystal particle size distributions. Here we have granules, so we have a population of granules, each granule having a population of crystals inside it, and so on all the way to the capsule. So populations within populations within populations. And that really needs a step change in the technology of handling these things. There's also, again, a significant contribution that process systems engineering can make at the component level. I'm not talking about the equipment, process equipment, that's what we normally have to do, but here, at capturing essentially biological behavior in the form of models. Again, there's a lot of activity going on in this area already. We're not inventing this. What we are bringing in, though, is a more systematic systems approach in terms of what makes sense, how do you relate in vitro experiment information with in vivo performance and vice versa, and so on. So there would be a huge benefit in us getting involved in there. The only word of caution is, if you go in there, you really have to go with a full commitment. Our superficial involvement in the past in various areas like this has not been entirely successful, to say the least. I still remember some of the work in the systems community, including some of the stuff I've done, I should say, for example, in reactor system synthesis, where because we failed to engage very deeply with what is a real reactor, what does a real reactor look like, and so on, the solutions we came up with were just mathematical artifacts, and so on. And we don't want the same thing again. And that's something we really need to be careful. When we go into these new areas, we really need to go in and devote ourselves to it. The third and final point I want to make is about the usage of how we use these process modeling calculations nowadays. Okay? We build these models. It takes an enormous effort, one way or another, to build them. What do we do with them? And really what we do with them, if you take the very high-level description of a system and a level, we have environmental inputs which we do not control, we have decisions which are under our control, and we have the key performance indicators we care about. And what we do is point calculations. We build this model, as I said, and we perform a calculation. It could be a simulation, it could be an optimization. We pick a point in this space here, let's say in a simulation, and a point here, and that translates into a point there, okay? So what we have there is a sort of point calculation. And then we do another one, and we do another one, and so on. Now, this, in my opinion, and in many other people's opinion, represents a huge waste of opportunity. There's a huge amount of information in these models, and at most, what we do is we investigate a dozen or a couple of dozen situations, yeah? Really what we want to do is to move to a different kind of paradigm there. And what we really want to see is, first of all, is to realize that what we should be interested in is understanding the global system behavior over entire spaces of inputs. Some of those inputs could be deterministic, like the ones that are under our control. Some of those could be probabilistic, like environmental inputs. And really what we are looking to achieve and to determine is not single numbers like we do now, is probability distributions in view of these probabilistic inputs. Now, so this is the kind of mapping we're looking for. Now, we have to realize, of course, that we don't have the system, we have a system model. So the model itself is uncertain. It has uncertainty in terms of the parameters, in terms of structural uncertainty, of course, very often. So this is really the kind of picture we should be looking at. Now, once you go to this point, you have to be careful because the answers you will get, just as before, will depend on the inputs you put in. In particular, the quantification of uncertainty both here and here is problematic at present. What I'm showing you here is a kind of very, very standard thing you get out of the confidence ellipsoids, the kind of assumptions we make, this is not really what you want to do. Increasingly, we're able to use techniques based on Bayesian estimation. I know Matthew has a whole talk on Bayesian techniques, but increasingly using techniques based on Bayesian estimation, like MCMC, Markov chain Monte Carlo, we are able to get much more accurate representations of the real uncertainty data. Invariably, I should say, all the examples I've seen so far, this is actually much smaller than the confidence ellipsoid approximation gives you, which is reassuring, but you can't take it for granted. The other thing is up here, where of course we are looking to quantify the uncertainty of the inputs, of the external inputs. And again, this is where this big data thing that's being talked about, mining those big data, mining whatever data is available, is very important in terms of quantifying uncertainty in future demands in various other environmental conditions. So, and once you do this, okay, we don't go into this, there's the issue of risk management, which is, okay, you know the answer now, what are you going to do about it? Which of these inputs are you going to try and affect, or how are you going to modify the system to do this? And there are techniques like global sensitivity analysis, which give you this. So this is what we are looking for. What are the challenges here? Well, some of the challenges are very mundane, like computation. This takes enormous amounts of computation to come up with this thing, no matter how you do it, whether you do it with deterministic chaos expansions, like Greg McCrae was talking about here many, many decades ago, or with Sobel sampling, which is what we use nowadays. What are the opportunities? The opportunities is a huge opportunity, of course, in terms of getting an understanding of the behavior of the system to an extent that you cannot really do in any other way. But really an interesting question, especially for the audience in this room, is what is the relation of these things with optimization-based methodologies? Most of us come from this background, maybe going back to Roger Sargent, which is what you have to do is pose the right optimization problem, pick the right objective, the right constraints, find the right algorithm for solving it, we solve it, and we get an answer, and that's it. And I have to say that when first all these ideas of global system analysis were posed to me, and should we do something in this area, I had exactly the same response. That's for guys who don't understand optimization. You don't want to do any of this, you do this. I changed my view slightly recently when I saw the results of a big model being analyzed with 800,000 samples in 17 minutes. And when I looked at how much information was there, and it began to dawn on me, there's no way you can get this amount of information, this amount of insight, if you wish, in any other way. So does this mean we're going to replace optimization with these things? It's going to be a pity given all the clever algorithms we have and so on. I don't think so. I don't think it's a question of replacement, but it's a question of complementing optimization, okay? When we have the problem, at the point when you have the problem very well formulated, the constraints we have well characterized and so on, maybe what you want to do is to solve an optimization, a global optimization problem. But until you get to that point, this kind of technique is really what you need. And I never thought I would say these things myself, but that's the conclusion I reached now looking at what's coming out of this kind of analysis. So just to conclude, as I said, these are just three, not randomly chosen, but three areas. There are many other areas where we can see significant improvement. But I'm confident that these three will actually, at least on their own, if they get realized, will result in a step change in our capability based on process modeling. Just to finish, I'd like to say something about the impact of enabling infrastructure. I think high-performance computing is key to this. High-performance computing is what enables us to go from the single plant to modeling half of Iraq in a single model and getting answers within an hour, which we can implement on a day-to-day basis. Okay. And there are analogies with Manfred, the example you mentioned from Raft Andrea with the thrown ball example, where they're doing 10,000 computations in 20 milliseconds. Okay. The availability of high-performance computing changes the perspective. It is MPC, but not as we know it. And GSA, to some extent, is optimization, but not as we know it. Okay? And so this is the kind of thing which will enable the new types of calculation like those and so on. And the only other one I want to mention, I don't want to talk about Internet of Things and so on. There are other people who will be much more qualified to talk about it. But we hear a lot about cloud computing, which could means anything you want to anybody you care to answer, you get different answers. So for some people, it's just a way of outsourcing the IT system to Amazon Web Services. Really, from the point of view of process modeling, there are two implications. First of all is the ability to go and get access to high-performance computing resources instantaneously, essentially. So essentially, we're back to there. But the more interesting one is this one here, that the way now many of the major companies are organizing their clouds will mean that the models have now instant accessibility to all the data they need. And that significantly reduces some of the model construction effort, okay? So we get into a sort of data-centered world where the models really are just transformations between this point of data in the web to that point of data in the web, on the cloud, sorry. So all of these have profound implications for the architecture, the design of the kind of software that people like me and others are designing. I don't have the time to go into this. I hope this has given you an overview of what I think is happening and where I think it's going. I will probably be proven wrong, but that's how it is. In the meantime, all I can do is, George, wish you happy birthday. Thank you for inviting me for this presentation, and all the best. Thank you.
Got time for a couple questions? Yes, Naz.
Thanks for the great overview. I have a question on the biopharmaceutical tablet manufacturing, if I could go back to that. You have, for example, let's say that you make a pharmaceutical product and you go for FDA approval,
yeah,
and it doesn't get approved. Now, my question to you is, through this modeling, because you're going forward modeling, can I go back and say what the cause might have been through modeling PSC tools to do more or less inverse models?
Yeah.
Because it's a nonlinear mapping, I'm not sure if it can be done, but I'm asking you.
Yeah. So really, well, the FDA approval will be based on the clinical trials at the moment. It won't really be based on this model. One of the things you can use this kind of model to predict is what is the probability of a clinical trial being successful, given the variability in the population in terms of ethnicity. For example, America has 61% of European origin, we have 12% Hispanics, 12% African Americans, in terms of weight, in terms of gender, and so on. And one of the things we are beginning to do, combining this kind of model with the kind of global system analysis I mentioned before, is coming up with the probability of various things being successful or not, okay? So it's basically, this kind of model will hopefully stop you from going to that point, before you get to that point of failing. Yeah. There are other dimensions which have to do with bioequivalence of existing drugs and so on, with new formulations with existing drugs. Again, we're now beginning to see how these can be used there.
So Kostas, maybe I can ask you a question following on that. In your picture here, you show oral absorption as sort of the end point.
Yes.
Which one might think of as a pharmacokinetic question, right, of how the body affects the drug. But one, of course, has to take that one step further when you think about the pharmacodynamics and how you're actually influencing the body through the drug. Are you thinking about that?
It's the difference between a vision and the implementation. Yeah. At the moment, this is a vision, but the actual implementation, at least of what we're working on, only goes up to here. We do not even attempt to predict how a given drug concentration in the plasma will translate into a biological effect, into a therapeutic effect. Yeah. It's only a question of the knowledge here being available, okay? And really, the way we see this framework is a framework to take all available knowledge and try to integrate it, rather than just apply it in a sort of patchy way, the way it's been done. This will very quickly, of course, show you that there are many things you don't know, which you should know. So identifying the gaps is also very important.
Great. There was a hand that went up in the back. Yes, could you come down to the mic and ask your question? Giannis?
Not a big deal. At what point do real-time data assimilation and black boxes come in? Do they come a little
bit? So,
Yanni,
can you speak?
Oh, so real-time data assimilation and black boxes, when do they come in the process? Do they come at all? When do you see them coming in?
Real-time?
Data assimilation, yeah.
Are you talking about online kind of applications? Yeah. Yeah, so those were the things I decided not to tell you about. But basically, if we go back to this picture here, essentially the only way you can apply these kind of models to real-time operations is by, first of all, knowing where you are. So state estimation applied to very complex models of this kind is something which is a prerequisite for this kind of philosophy to be applicable to operations. Yeah. Now, we're doing some work in state estimation using first principles models. with some success and some failures. And, but yeah, it's a very important point.
And any black boxes anywhere or not at all?
There is no, in this picture here, there is nothing which says that we couldn't have a black box as a level 0 model, yeah? In the end, a model is just a mapping between inputs and outputs within a given degree of required accuracy. If you can achieve that degree of accuracy within the scope of the input variation, it's fine, it could be a black box.
Rephrase, last iteration. How about a black box for the model mismatch between the best you can do and the truth?
So indeed, I mean, it doesn't have to be a purely mechanistic model. It could be a hybrid model, yeah, combining first principles model with a residual being calculated using a statistical approach, a neural net approach, whatever, or something else.
Terrific. Well, would you please join me in thanking all the speakers from the first session for a stimulating session. We're obviously a little bit behind schedule. What we're going to do is take a 20-minute break. So at 12:15, we're going to resume the session.